Beneath the floor of every rainforest on Earth, a market is open for business. Prices are moving. Somewhere in the dark, a trader is hoarding stock to drive a price up, deliberately starving one buyer so it can gouge another. And the trader pulling it off has no brain, no eyes, no heart, and is thinner than a single strand of hair on your head. You have been walking over markets like this your entire life. Every forest, every park, every patch of grass you have ever stood on is sitting on top of one. And here's the most disturbing part. We only finished mapping the biggest ones last year, and we're already destroying them. To understand why that matters, you have to understand what is actually down there. Scrape away a handful of soil from under a tropical tree and it looks like dirt. It is not dirt. Threaded through that handful, wrapped around the roots and reaching out into spaces you cannot see, is a webbing so fine it makes the finest root look like a fire hose. These threads are called hyphae, and they belong to mycorrhizal fungi, the fungi that have been quietly running the planet's plant life for more than 400 million years. The thinness is not a footnote. The thinness is the entire weapon. A plant root, even a delicate one, is a clumsy thing in the soil. It can only push into gaps wide enough to take it. But a fungal thread is so vanishingly fine that it slips into pores no root could ever enter, squeezing through the microscopic plumbing of the soil and unrolling an absorptive surface so vast it can multiply a plant's reach many times over. These threads can make up as much as a third of all the living mass in the soil beneath a forest. A third of everything alive down there, built out of filaments you could snap with a breath. So the forest you can see, the canopy, the trunks, the leaves catching light 100 feet up, is not really the organism. It is the storefront. The supply chain is underground and it is run by the fungus. And it runs that supply chain like a commodities trader. This is where it stops being a nature documentary and starts being economics. Plants are very good at one thing, pulling carbon out of the air and turning sunlight into sugar. They are terrible at getting phosphorus and nitrogen out of the soil. The fungi are the opposite, useless at making sugar, brilliant at mining minerals. So they strike a deal. The plant pays in carbon. The fungus pays in nutrients. Carbon flows down, phosphorus flows up, and both sides come out ahead. Except it is not a friendly handshake. It is a trade negotiation, and the fungus negotiates hard. Researchers wanted to actually watch the trade happen, so they did something clever. They tagged phosphorus with fluorescent quantum dots, tiny beacons of light, and then sat back and watched where the fungus moved it. What they saw was not a charity, it was arbitrage. When the fungus found a patch of soil rich in phosphorus, it physically hauled that phosphorus across its network and stockpiled it in patches where phosphorus was scarce. Why move it to where it is rare? Because scarcity is leverage. In a patch where phosphorus is hard to come by, the plant is desperate, and a desperate plant will pay more carbon for the same fistful of nutrients. The fungus was manufacturing local shortages to drive up its own price. It gets worse, or better, depending on which side of the deal you are on. The fungus will sit on a surplus during a boom and release it later, when demand climbs and the terms are better, hoarding stock to sell into a rising market. This is a creature with no nervous system running a strategy that would get a human investigated for price manipulation. Think about what that actually requires. To gouge a plant, the fungus has to register that a patch is poor, that the plant is desperate, and that desperation is worth a premium in carbon. To stockpile through a boom, it has to hold inventory against a future it cannot see, betting that demand will climb. It is reading supply, reading demand, and timing the release, not as a metaphor, but as a measurable physical movement of glowing phosphorus across the soil. The forest's economy is not a poetic flourish laid over the biology. It is the biology. But the plants are not helpless in this. They have found the one move that works against every monopolist in history: shopping around. When a single plant is plugged into two competing fungi at once, something shifts. The plant can play them off against each other, and suddenly it gets more phosphorus for less carbon. Competition drives the price down. The whole thing, the hoarding, the arbitrage, the comparison shopping, is happening in the top few inches of soil, governed by nobody, written down nowhere, and it has been operating under your shoes the whole time. Which raises a question that should be impossible to answer. How does a thing with no brain run logistics like this? In 2025, a team mounted time-lapse robotics over living fungal networks and filmed them building themselves in real time, something nobody had ever properly seen. What they captured looked less like a plant growing and more like a city's traffic system waking up. Material did not just drift along the threads. It moved in flows, in traveling waves, surging and routing. And in a single strand, at a single moment, they watched cargo moving in both directions at once. Phosphorus heading one way, while carbon headed the other, down the same microscopic pipe without collision. The scientist who has spent years staring at this, Toby Kears, reached for the only comparison that fit. Watching the fungus decide where to send its resources, she said, was like watching the best poker players in the world play a game of poker. Reading the table, weighing odds, committing resources to the move with the best return. Strategic logistics played at a world-class level by something that does not have a single neuron to its name. And there is no boss, no control room, no central node giving orders down the line. The network has no headquarters because the network has no head. Every decision about where to push a wave of phosphorus, where to thicken a route, where to abandon a dead end, emerges out of the whole thing at once. A distributed intelligence with no place you could point to and call the mind. We build supply chains with managers, software, satellites, and entire companies coordinating the flow. The fungus runs a comparable operation with none of it, and has been doing so since before there were trees, before there were leaves, before anything we would recognize as a forest existed at all. And then there is the question of what it even is. We like to think an organism is one thing with one set of genes. You are you. A dog is a dog. But these fungi do not play by that rule. Their threads do not have neat walls dividing one cell from the next. Instead, the genetic material flows freely through one continuous shared interior, a single open channel of living cytoplasm running through the whole network. And drifting through that channel at any given moment can be thousands of genetically distinct nuclei, thousands of different genomes mingling and flowing inside what we casually call one fungus. So when you point at a fungal network and say there is an individual, you are wrong in a way that is hard to even put into words. It is not one genome wearing one body. It is closer to a river of mixed DNA, flowing through the dark, with no clear edge where one self ends and another begins. Now, this is usually the point where the story turns warm and fuzzy. You have probably heard the comforting version, the wood wide web, trees holding hands underground, mother trees nursing their seedlings, the forest as one big cooperative family sharing food through a benevolent fungal internet. Here is the uncomfortable part. A lot of that may not be true. In 2023, a paper in the journal Nature, Ecology and Evolution did something that took real nerve. It went through the popular claims about these networks, the nursing, the altruistic sharing, the kumbaya forest, and pointed out that many of them are simply not well supported by what we actually observe in real forests. Worse, the authors argued that even the scientific literature had picked up a bias, a tendency to cite the warm, positive findings and quietly overlook the studies that found nothing or found the opposite. The beautiful story had started to write itself, regardless of the evidence. So the truth is messier and a lot more interesting. Because when you look closely at what these networks actually do, they are not always sharing. Sometimes they are defending territory. In rainforest soil, an established, intact fungal network can act like border patrol. When researchers tried to introduce invading eucalyptus seedlings into soil already wired up by a resident fungal community, the network did not welcome the newcomers. It actively held them back, suppressing the outsiders trying to muscle in. The established plants, working through their fungal partners, were defending their turf. This connects to something foresters have known for a long time without fully understanding it: the ashbed effect, where certain seedlings only establish themselves easily after a fire. Now look at it through the network. The reason fire opens the door is that fire burns the network. To let a new competitor move in, you sometimes have to destroy the incumbent infrastructure first. The fungal web is not just a trade route, it is a moat, and the residents will use it to keep you out. So this is a system that hoards, gouges, defends borders and suppresses rivals. And yet, when the threat is right, it can also be the fastest warning system in the forest. Watch what happens when aphids attack a bean plant. The plant under attack is wired into its neighbors through the fungal network, and as the aphids start feeding, a signal travels down the threads to the plants nearby. Before a single aphid has touched them, before they have any reason to know danger is coming, the connected neighbors start manufacturing defensive chemicals. They pump out volatiles, including a compound called methyl salicylate that does two jobs at once. It repels the aphids and it summons the parasitic wasps that hunt aphids for a living. The neighbors raise their shields and call in air support, all from a warning that arrived underground. The control group is the part that gives you chills. Plants of the same kind, the same distance away, but not connected to the network, got nothing. No warning, no defense. They sat there exposed while their wired-in neighbors armored up. The difference between safety and slaughter was a thread you cannot see. And some organisms have looked at this entire system, the trade, the warnings, the shared wealth flowing through the dark, and decided to stop paying in. There are plants that have quit photosynthesis completely. They have abandoned the green machinery that defines what a plant is supposed to be, and many of them have lost their color along with it. Ghostly, often pure white things pushing up out of the leaf litter with no chlorophyll at all. They are called mycoheterotrophs, and they are thieves. Roughly 600 species have given up making their own food entirely and live their whole lives feeding off the fungal network instead. And that is just the ones that quit forever. More than 33,000 plant species lean on fungi for survival, at least when they are first germinating, before they can stand on their own. But the strangest proof of what these ghost plants are doing came from an unlikely source: nuclear weapons. When countries tested atomic bombs above ground in the 1950s, they spiked the entire atmosphere with a pulse of radioactive carbon, a chemical fingerprint stamped onto a specific window of time. Scientists realized they could use that fingerprint as a tracer. They went to certain ghostly orchids that survive entirely off the fungal network, and they read the carbon inside them. And the carbon did not match a living tree. It matched decaying dead wood. These orchids were running on carbon that had been pulled out of the air decades earlier, locked into a tree. That tree died, and the carbon then flowed through the fungus and into a plant that was alive today. A living plant, breathing on air that was fixed before its own existence, delivered by a thread. There is no other way for that plant to exist. It cannot make its own food. It cannot reach that buried carbon. It has bet its entire life on the network being there, doing its job, moving inventory it will never see. Cut the thread, and the orchid does not adapt or struggle on. It starves in the dark, surrounded by a forest full of food it has no way to touch. It is the most total dependence on hidden infrastructure in the living world. And it is everywhere, pushing up pale through the leaf litter, hiding in a plain sight. So step back and look at the full machine, a market that hoards and gouges, a logistics network that plays poker, an organism that is a river of thousands of genomes, a border force, an early warning siren, a black market supply line feeding ghosts on decades-old carbon, all of it running on filaments thinner than hair. in the few inches of soil under the forest floor. And then you find out how much it is actually moving. A meta-analysis put a number on the carbon that plants funnel down into these fungi every single year, and the number does not sound real. Around 13 gigatons of carbon dioxide equivalent. To translate that, it is roughly 36% of the carbon we release by burning fossil fuels worldwide every year. More than a third of humanity's emissions pumped into the ground through hair-thin threads, where a large share of it gets locked into the soil and held there. One of the single biggest carbon sinks on the entire planet is made of fungal thread, and until recently it was almost entirely left out of our climate models. We were building our predictions for the future of the atmosphere while ignoring the part of the carbon cycle that handles a third of our own output. The infrastructure was load-bearing, and we did not even have it on the map. Sit with the engineering of that for a second. If a structural engineer designed a bridge and forgot to account for a third of the load, that bridge would be condemned. We have been modeling the future of the only atmosphere we have with a gap that large. A sink so vast it rivals our entire fossil fuel output, run by an organism we are only now learning to see. And the moment we finally started to see it, we found out where the most irreplaceable parts of it live. Which brings us, finally, back to the thing open for business under your feet, and to the reason any of this is urgent rather than merely strange. In 2025, a group called SPUN published the first high-resolution global maps of these underground networks. To build them, they sampled and read more than 2.8 billion fungal DNA sequences, gathered across 130 countries, the first time anyone had seen the shape of this hidden half of the planet. And the maps showed something that should change how you feel about the next forest you see cut down. The rarest mycorrhizal networks on Earth, the most unique, the least replaceable, the ones found nowhere else, are concentrated in the rainforests of West Africa and the temperate forests of Tasmania, the exact places where the chainsaws are loudest. And about 90% of those biodiversity hotspots sit completely outside any protected area. No fence, no status, no law standing between them and the next clearing. We are cutting down the rainforest's hidden half before we have even finished discovering what exists there.